Hello, students. We're going to jump into section 2.1. Again, I've covered chunks of this in class. I'm not repeating what I covered in class. I do want to highlight a few of the key pieces where I think students tend to struggle, and we'll go from there. All right, so let me go ahead and share my screen. And let's see here, we'll get into Canvas. All right, should be up now. So in Canvas, remember I've got kind of my video pieces here, and the homework is down. So I'm going to click on the homework list. I did try to add a tentative due date. Remember, it can kind of change. So for example, 2.1, we would have had it due on the 6th of September. And it looks like it's way back, but it's just kind of because the 6th is a Wednesday, it would just wrap around to the following Monday because I haven't finished the components of 2.1. So that's the big idea there. And again, I've added some of the homework for the next few chapters as well. And we'll see. Hopefully this works out well for everybody. So we're going to talk about 2.1. And let me go ahead and switch over to the whiteboard here. Okay. Grab my pen. So we've talked about in class some of the big ideas. The three big pieces to this point that we've covered are the and, the or, and the negation. Okay, so for example, if we had two statements and we said P and Q, this is what we would say, P and Q, and we would write it with that little symbol though. So this is and. The next one is the or, and as I mentioned in class, this is the inclusive or. So that means at least one of them has to be true. So for an and statement, all must be true. I gotta pick up another pen next week, I think. All must be true for P or Q. At least one must be true. Must be true. So for an and statement, it's actually very easy for the statement to be false, right? Because if at least one of them is false, the whole thing's false. For an or statement, it's very easy to be true because at least one of them must be true, making it harder for it to be false. And don't forget, like the negation, this would be very quick. It's just the opposite, right? So if P was true, then not P, or the negation of P, would be false. So this is the not. Okay, so those three, again, they aren't too bad. Usually students are okay with these three chunks. Perhaps if I was to say, what's the hardest one, Scott? I'd probably say this one, but only because you have this other idea of an or statement. When someone says or, a lot of people think of it as one or the other, and that both of them can't happen. Okay, so for example, if I said, it is sunny and I am happy, remember both of those have to be true. I look outside right now, it's cloudy, but I'm clearly happy. So that whole statement would be false. So then if we did something like this, though, I am happy or it is cloudy, because that's what it is today. I'm looking outside. So if I wrote this statement down, notice that in this situation, you'd say, let's see here, is Scott happy? You'd say, okay, that's true. Okay. Is it cloudy? You'd say that's true. And the symbol in the middle is the or symbol. So true or true. And kind of remind yourself, hey, I just need at least one of them to be true. And so this would actually equal a true statement, be equivalent to a true statement. Right? So let's see here. So there's kind of those components. We've talked about, I think I did a truth table in class. Let me do one other truth table now. Woo, let me come down here and get a new page going. All of a sudden my cursor disappeared. Not great. Okay, so here's the idea. Now remember, truth table is kind of a way of, from the problem solving chapter, making a list of everything that could happen. So if we have statement P and statement Q, ooh, good straight line there. Okay. Remember, statement P could be true or false, but so could statement Q. So we could have, what we do is we tend to write two true statements down for Q in a row because P could be true or false when Q is true, or P could be true or false, and then Q could be false. Okay, so what we've done is we've listed every possibility. And if you think about it, for P, there are two options for P, true or false, and there are two options for Q. And for each of them, we have to match them up. This would be multiplication, and that's why we get 4. So for one statement, there is 2. For two statements, there are 4. If we had 3 statements, it would be 2 times 2 times 2, which would be 8. And you get this beautiful geometric sequence. I know, chapter 1 coming back again. All right, well, let's take a look then together. All right, so what I'm going to do now is I'm going to kind of mix it up a little bit. Okay, so I'm going to put one that we did in class. We already did this one, but I'm going to leave it off because we already did it, right? And then I'm going to do this one like that. Oops, let me close that off. There we go. Okay. And then I'm going to throw a couple in here that we did do in class, but also they're just like super quick. Okay. So don't get too worried about those. Okay. And then why don't we do this one? Ooh, not P. Okay. We're going to link those together. All right. Phew. All right, so now here I'm going to use blue as we go through the table. So let's start with this one right here. So this says I want to negate P and Q. So you can do it mentally if you prefer, but if you want to, you can also write out the original statement P and Q, figure out the truth values there, and then just negate that column. Now, some students find it quicker to write the extra step and then negate. Me personally, once you get used to what an and statement is, which remember, and statement needs all have to be true, right? All have to be true. So when I look at the and statement, here's what I'm looking at. I'm looking at the two statements, P and Q. I notice they are both true. So what I do is I come over and I write a false statement because I'm negating it. Okay. Remember, both of them were true. If there was no negation symbol, it would be true because they're all true, but I'm negating it. Okay, so now P and Q. If I come down here to the next one, here I'll put a little box around that. So now I'm looking at this next one. I have false with true. Remember, they all have to be true. They're not, so that is false, but I have to negate it, which means the entire thing is now true. Tap and true. Okay. Same for the next one. They both have to be true. They're not, so it's false, but I negate it, so I get true. The last one, false, false. They both have to be true. They're not, so it's false, but I negate it and I get true. Okay, so that's the one-step approach. Now, I have a feeling some of you, if you're watching this video, you're like, what the fudge? What's that, Fallstrom? Okay, hold on. Let's go back. Let's go back and try it with the other approach. So let's come and complete this column first. And statement. True, true, I would say true because they're all true. False, true, I would say false, right? True, false, I would say false. False, false, I would say false, okay? So if you complete that column first, then notice the only difference between the two is I'm now negating that entire statement. So if you want to negate something, what do? You just write down the opposite truth value. And you could kind of then say, oh, okay, I see exactly how you got those. Okay, your choice, your choice. The one step or two step, doesn't matter to me. Okay, let's continue on. Let me erase. There we go. All right, here we go next. Now, what I'm going to do next is you could come down to this very last column and try to do this all at once. that's up to you. An or statement, remember, at least one of them has to be true. So you could do this by looking at statement P right over here, taking the negation of it, it is false. Looking at statement Q, taking the negation of it, it's false. And then saying, okay, that's not the case. So this would be false, right? For most students, I think that might be a bit much. So I put in these two columns next to it. I'll mark them with a star. And if you do these two columns first, then you can kind of put your finger kind of rolled down, put two fingers and kind of roll down one at a time to figure out that final column, because now you're just looking at the or statement. Remember, or at least one must be true. Okay, at least one. All right, so if I do negation of P, all I do is come over to the P column, find the entire column, and just negate every one of them. So it goes true, false in the P column. I just negate that, and I would write false, true, false, true. And the same for negation of Q. Find the Q column and just negate it. So I would write false, false, true, true. Okay. Now, what I'm going to do is I'm going to highlight these two pieces because that's negation of P, negation of Q. The statement is an or statement. So I tell myself, is at least one of these true? And I look, it says false, false. They are not, it's not the case. So when I write down my final solution here, I would write false. Then I simply move down and do the next two. True, false. Is at least one of those true? And the answer is, yeah, at least one of those is true. So I get true. Repeat that process. Again, this is if you have these written out on paper, just move like two fingers down to the next one. False, true. False, true. Is at least one of those true? Yeah, it is. Okay. And finally, move down to the very bottom. You've got true, true. Is at least one of those true? This is the most common piece. Students would write false because they're like, it says or. Remember, we are doing an inclusive or, so I would write false, true, true, true. Okay. All right. And that is how you can do these truth tables. Figure out the pieces you need. If you need to write extra columns like I did here, put them in. Make it easier on yourself. And now let's take a peek here because there is something to take a look at. I want you to take a look at this column right here and this column right here. And what I want you to notice is not just that they have the same values at some point, they have the same values for every single row. And when things have the same value for every single thing, we call them equivalent. So we would write it this way. The negation of P and Q is equivalent to, notice I'm not putting an equal sign. I put an equal sign with an extra line underneath it because these aren't numbers. You see that equal sign is when two numbers are the same. This is a symbol for equivalent, and it doesn't have to be numbers now. Okay, these are two logical statements. And so here we go. I would say these two are equivalent. And if you kept going, there is another one where you say this one, P or Q, and that turns out to be equivalent to the negation of P and the negation of Q. Okay, these have a fun name. These are named after a German mathematician named Augustus de Morgan. And so Augustus de Morgan, these are called De Morgan's laws. Just like we got to have Brooks' rule in class, these are called De Morgan's laws. Okay, so these are two things that are pretty helpful for us. And it is a little hard sometimes to remember these, but if you go back to the quantifiers, these are basically dealing with the quantifiers. So remember, for an and statement, all of them have to be true, right? But if you negate an all statement, then it turns into a sum, and we would say some are not true. And that is why you'll see the negations here. Some are not true, meaning at least one is not true. Okay. And that hopefully makes sense too. Remember, this statement was an all statement. In order for the whole thing to be true, all of them had to be true. So if it is not true, then at least one of them had better be false, or better be the negation of that. There's the concept, the idea behind it. Let's come down here. This is a sum statement, which means at least one of them must be true. Hold on a second. My neighbor's umbrellas are going to blow into their house. Give me 1 second. I got to pause the video. Phew. Okay. Sorry about that. You know what? Because I paused the video, to all of you watching, looks like I wasn't gone at all. So yeah, just ignore that glitch. We'll get right back to the math. All right. So let's see here. This is a, I gotta remember where we were. Oh, this is a sum statement. So at least one. And remember, if you negate an at least one, you have to prove that all of them are not true. So again, if you think about that idea that we talked about in class, we can tie it into this new rule, as they call it, De Morgan's rules, De Morgan's laws, and it kind of connects, matches up really nicely. So it's not like it's a new thing. I guess that's what I'm trying to say. All right. Let's see here. The last piece, and probably the one, again, I said there's usually one thing that kind of gets students to get a little bit stuck, is probably the idea of an if-then statement. So again, this is a different type of statement. It does have a fancy name. This is known as a conditional. Let me make sure I spell it right. Conditional. There we go. Statement. So let's see here. If it is sunny, then I am happy. Okay. So that is how we might say that. So if it is sunny, then I am happy. Okay. I type quicker than I write. Okay, so there it goes. Okay, so how would we code this? We might say the it is sunny, which is a statement. We might say, okay, that's the statement S. Okay. Over here, then I am happy. So maybe that's the statement H. Okay. And then for an if-then statement, we draw an arrow. Okay. And that goes from the hypothesis, that's the first piece here, hypothesis, to the conclusion. And I usually like to think, so for me, no, that's the official term, I like to think of this one as being the condition. Okay. So like if it is sunny, so what am I checking? I'm checking this condition. And it's if it is sunny, then I am happy. So in order to determine the truth value of this, we have to look at the individual components, right? And it's helpful to be thinking of what it would take to prove this false, okay? Let's see here. So we might be able to do another one like with an all statement. Okay. So if it is sunny, so all sunny days. So if it is sunny, then I'm happy. That's like all things are sunny are inside of this thing that makes me happy. Now, it's important to note that it does not say that the only time I'm happy is when it is sunny. It doesn't say that. It says, if it is sunny, then I am happy. There might be a lot of other ways that you're also happy. Maybe if someone gives you $100, you are happy, right? I mean, so there's a lot of other things. This is just a condition that gets you into this other piece called happiness. So if you want to kind of visualize it, picture this. Like if there was a big thing over here of all the things that make you happy, right? And inside of that, right, is this other thing called sunny, right? So when we think of this, it's like if it is sunny, so if there's a little dot right here, if the dot is sunny, guess what? Then it's inside the happy circle, right? Okay. But notice there's other things that could make you happy. Over here is the $100 bill, right? You find a $100 bill, you're like, woohoo. Okay, so that makes you happy. That doesn't mean that it's sunny on that day. It just means the $100 made you happy as well. So there's things that make you happy, and a group of those are it is sunny. Okay. So keep that in mind as we consider this, what it takes to kind of make something like this false. Okay. All right. So let's see here. Yep. I'm gonna choose a different one that might fit more with some of you. I'm gonna choose a different wording. So this this one seems, at least this one stuck with me growing up, and maybe it doesn't stick with you. If you miss curfew, then you are grounded. Okay. This is an if-then statement, right? It is. If you miss curfew. So maybe growing up, you grew up with a curfew. I know I had a curfew growing up. So this would be like, if you miss curfew, then you are grounded. Okay. So this could be statement P. This, you are grounded, is going to be statement Q. I put the if-then statement between them. Okay. And so what we're going to do now is I'm going to make a truth table for this, right? I want you to think about all the options that could exist for statement P and statement Q. So statement P, let's see here, could be true or false. We know that. Remember, statement Q could be true, and then statement P could be true or false, while statement Q is false. So you have to look at all these different situations. So each one of these situations, if you will, forms an interesting little group. So we have to kind of put that into words. Okay, so this first one, remember, someone has made this claim. They said, if you miss curfew, then you are grounded. So you can think of this as like being your parent. Okay, a parent made this statement. Now let's go see what happened on a particular day. And that's what we're looking at here. Okay, so let's see here. Did you miss curfew? True. Then you are grounded. Yeah, you got grounded. Oh, so now we go back and review that statement from your parent. Your parent said, if you miss curfew, then you are grounded. You'd have to look at that and you'd say, well, I sure can't prove it false. That is absolutely true. Okay. Let's move down and try this next one. Okay. If you miss curfew, then you are grounded. So the first part is, did you miss curfew? And statement P is false. You did not miss curfew. You did not miss your curfew, and yet you still got grounded. So if you remember those circles, yes, your parent is saying, if you miss curfew, then you are grounded. They're not telling you the only way you get grounded is missing curfew. They're telling you if you miss curfew, then I guarantee you're going to get grounded. That's what they're saying. So maybe you could say, wait, I feel like they're lying to me. I did not miss curfew and I still got grounded. Well, yeah, you drove the car 90 miles an hour to get home and you drove through the mailbox and the car's all scratched up now. Something like that, right? Okay, so the parents, yeah, you're grounded anyway. So look at their statement. In order to disprove their statement, we have to find a case when that does not work. And that did not work here. They did not lie to you with this statement. Let's come down here to the next one. If you miss curfew, then you are grounded. Okay, let's see here. Did you miss curfew? Yes. Did you get grounded? Look at Q. No, you did not get grounded. But your parents said, if you miss curfew, then you're going to get grounded. But you didn't get grounded at this point, even though you might appreciate this. This is false. Okay. And the last one. Did you miss curfew? No. Did you get grounded? No. Then their statement is not a lie. Basically, the statement just didn't apply to you at all. None of that did. So we can't go back and say that the statement up top was a lie. It is not a lie. So if it's not a lie, then it's true. Remember, statement is either true or false, but not both. So there is one situation where the original statement is false. And for every conditional statement, there is one way that it's false. You have to meet the condition and fail the conclusion. Okay. So here's something from my daughter, right? This was around the age of, I don't know, 16, 17. Maybe you said something like this at some point too, right? If you love me, then you'll buy me a car. Well, I do love her, but I did not buy her a car. So that statement is where I would be able to say, do I love her? Yes, I love my daughter. Did I buy her a car? No. I met the condition. I failed the conclusion. So I would say that her statement is false because I met the condition and I failed the conclusion. Okay. All right. That's the idea behind the if-then statement. Now, there are some other components to an if-then statement, other ways of thinking about it. There's other ways to write it, but you can actually see those in the book. I'm not going to go through each one of those. And so we have our statement. Let me type these out. I think it'll be easier. So we have our statement. And this is a conditional statement. I'm going to put that in parentheses. And the statement could be if, let's see here, what this, we'll go with if the sun is shining, then I am happy. I'll go back to that one. Maybe some of you don't want to hear about people getting grounded. Okay, there's my statement. All right. So I want you to think about that. I have a condition, the sun is shining. I have a conclusion, I am happy. All right. Now, if I turn that statement around, it is actually called something else. So if I write, if I am happy, then the sun is shining. Okay. So if I write that backwards, it is not called the conditional statement anymore. Now, technically, it's still a conditional statement. It's still an if-then statement, but we phrase it different from the original. So if you have an original and somebody switches it around, we have a term for it, and that term is called the converse. Okay, so if you take a statement, and let me write that down in symbols over here. Let me do that next to it in blue. So here, like the sun is shining, then I am happy, right? If I reverse that, if I'm happy, then the sun is shining, it looks different. Okay. And if you want to see why these are actually different statements, we go back to what does it take to make it false? I have to meet the conclusion and fail, meet the condition, fail the conclusion. So true starts, then false. That would make this statement false. But if I come down here and I do false for Q and true for P, well, then I didn't even meet the condition. So whatever my conclusion is, it could happen or not happen. It has nothing to do with my statement. So we could not prove it false. This would have to be true. So you can see those aren't lining up truth value wise. And that's why these two are not equivalent. Okay. All right, let's go down. We'll do a couple more. Now here comes the other fun one. So what happens is people love doing some of these and then changing things around. So now if you change things around and you say, what if it's not shining, right? So if the sun is not shining, then I am not happy. So again, a lot of times it's quick to say, oh, well, that's the same thing as the original statement. But let's check and see if it is the same, right? This has a fun word as well. So we actually call this one the inverse. Okay. There we go. So the inverse is you take the original statement that you had and you put a not in both of those statements as you read across. So now it's if the sun is not shining, then I'm not happy. Okay, if you want to write that one out in code, that would be not P arrow, then not Q. Okay, and remember what made this one false was this. So now if P is true, the negation of P is false, the negation of Q is true, and I end up with false true. Actually, that was exactly what we had here, false, true. So the only way to make this false is to meet this exact piece. So this is the interesting thing. They're not equivalent to the original statement, but the converse and the inverse are actually equivalent to each other. That's kind of cool. All right, let's try the last one, which is, what if you negate both of them and then you flip it around? So again, the converse flips it around, the inverse negates them. And so if you do a converse and an inverse at the same time, what does that look like? And it actually has a fun name. It's called the contrapositive, which would say, if I am not happy, then the sun is not shining. So I do both of those things. I flip it around and I negate it. So if I came over here and wrote the contrapositive out, it would be, if I'm not happy, then the sun is not shining. Looking back and say, okay, if P is true and Q is false, that's how I make the original false. Coming over here, if Q was false, then not Q would be true. If P was true, then not P would be false. And notice I've met the condition, I've failed the conclusion. This one is false, which means this last one is equivalent to the top one. And so the original statement, P then Q, is equivalent to the negation of Q implies the negation of P. Now let's try to think about that for a moment, right? Think about the original statement. If the sun is shining, then I am happy. Okay. So if you're not happy, well, then I don't know much, but I do know that the sun is not shining, because if the sun was shining, you would be happy. So because the sun is not shining, I know you are not happy. So if I'm not happy, the sun is not shining. If the sun is shining, then I'm happy. So that's how we can kind of relate these two pieces together. And that's why they're equivalent. We can show them in a truth table if you prefer. I was trying to do more of an explanation on this one. And we can do other ones too. So let's see here. If you get an 87%, then I assign a B. Okay, so this is on, if you look at our grade scale on the class. If you get an 87% in the class, then I assign you a B. Right. So now you could analyze this statement. You can say, okay, so let's see here. If I did get an 87% and Scott gave me a B, well, then that's true. So I can't prove that statement false with that, right? You have no complaint. There's no complaint that you could make against me. The question is, when could you make a complaint against me? And so I want you to think about that. When could you make a complaint against me? You could make a complaint if you did the 87 part. You got an 87, and I did not assign you a B grade, right? And some of you have been in this boat perhaps in the past. You thought you got this grade. You look at it, looks like you got this percentage. The teacher gives you a C, and you kind of get a little bit cranky, right? Right. And noticeably so, because you would say, hey, you said if I get an 87%, then I get a B. But I got the 87. You didn't give me a B. So you want to say the statement is false. You probably use stronger language. You might say some swear words at that point. Okay. So that's when you could prove this false. You did what you were supposed to do. You met the condition. And this word here, the if statement, tells you this is a condition. It doesn't say you always get a B, does it? It says if you get an 87%, then I will give you a B. Okay. Now think about the reverse of that. What if I gave you a B? Does that mean you got an 87%? So if I reverse that, you'd have to say, no, that doesn't mean that. It doesn't mean that if I switch them around, it has to be true. Because if I got a B, maybe I got an 88%, or maybe I got an 85%. So there's other ways I could get a B. Scott is just telling me if I happen to get this exact grade, then this is the conclusion that I can expect from it. Okay, so that's the way those tie together. Okay. And let's see here. Last piece, there are some times where we do mean a two-way street, where we actually mean that if P happens, then Q happens. And we also mean that if Q happens, then P happens. Okay. Right. So let me give you an example with numbers, right? If a number ends in a 0 or a 5, then the whole number, no matter how many digits it has, is divisible by 5. So if it ends in a 0 or a 5, then it's divisible by 5. And guess what? If it's divisible by 5, then it ends in a 0 or a 5. So that's a statement where you could switch them around and they're both true. So this, we create a new symbol. So if you look at that, see the arrow going from P to Q, then an arrow going from Q to P. We actually call this a biconditional statement, and we introduce kind of a new symbol. And that is the symbol right there. And we actually have wording for this. This wording here, we say if and only if. So if and only if is how we read the biconditional. So that would be if, so it would say what? A number is divisible by 5 if and only if the number ends in a 0 or a 5. And the reason why I'm using all this precise language is we're going to use it the rest of the entire course. Mathematics is built upon logic, so we can't avoid it. And if you're looking for some of these pieces, as we'll see in the next day of class, we are going to do some logic and reasoning with these. And so if you have an all statement, like all dogs are yellow, as an example, right? You could build a picture for that. So you could say, okay, well, here's all the dogs, and here's all things that are yellow, right? Because I know that all dogs are yellow. The statement doesn't mean that everything that's yellow is a dog, right? Just like a conditional statement. But I would know that if it is a dog, then it is yellow. So this all statement you can think of as what? A conditional statement. If it is a dog, then it is yellow. Now, I could give you the first statement. I could give you a second statement. I could say something like, Coco is a dog. Okay. So now if I come over here and I say Coco is a dog, so I could put a little dot right there and say, okay, now here's Coco. What do I know about Coco? Could I make the conclusion that Coco is yellow? Question mark. Is that going to be guaranteed? So what that means is if these statements are true, and I want you to think of those like conditions, can I guarantee the conclusion also has to be true? And let's see here, if Coco is a dog, then Coco is in this larger circle here, which is things that are yellow. So I would have to say true. If the first two are true, then the conclusion must follow. And that means we would say that the reasoning skill here is valid. This would be what we would call a valid argument. You make some claim statements, and if those claim statements are true, we look at the conclusion and we try to figure out, can I guarantee the conclusion? And that's how we have valid. Okay. Well, let's look at one more similar. Okay. All dogs are yellow, right? And I will now say, what do I want to say? Oh, my dog. Evie is yellow. Okay. So what I want to do is to compare the reasoning here and determine the statement. Okay. Now for the reasoning, this is where Sometimes people get a little a little worried about this. For a statement trying to determine whether the reasoning is valid, is the argument a valid argument, we build this and we assume that both of these are true. So I need to build a picture that says all dogs are yellow. Okay, so once again, here's dogs. That's all dogs. And here's everything that's yellow out here. Okay, got it labeled. I know that Evie is yellow. So the question now is, where should I put Evie? I know that Evie is yellow. So notice Evie could be located here. Evie could be located here. As long as Evie's in the yellow circle, Evie could be anywhere. Okay. So if Evie is in this second component, right there, then the first two are true and the conclusion is true. So that works out pretty nicely. It looks like things are great, looks like valid. But here's the thing with reasoning, just like with conditional statements. If you can find one time, one counterexample, then the entire thing doesn't work. Now notice to the right-hand side, I've got a case over here where there's Evie. So if I erase the entire first one, I can show you a picture where Evie is yellow, but Evie is a dog becomes a false statement because Evie is outside of the dog circle. So I've met the conditions. I've failed the conclusion. I would say, let me change color just so it's a little bit more clear. I would say this is invalid reasoning. Okay. We cannot guarantee the conclusion is true. Okay. And that's the only time we're looking, folks. That's it. The only time we care is when we meet the conditions and fail the conclusion. So if you look for that one situation, that happens, we say invalid. If that doesn't happen, it's valid. Let's see here. Yeah, there we go. Now, that doesn't necessarily mean that your statements up here are true. Okay. The statement, all dogs are yellow, is not a true statement. You could give me a counterexample by finding a dog that is yellow. Okay. I think in another class I did some cats are green. I think it's what I call it. I think I said that. Some cats are green. And people were like, nah, it's not possible. And then I went out and looked online and I found an actual green cat. Oh, I wonder if it's still out there. Green cat. Yes. Yes, still there. So it turns out that the cat was actually living near a like a chemical plant. So this chemical plant produced some byproduct, and the cat was kind of sleeping in this and turned the fur completely green. So green cat. So anyway, that's the the story. You know, if it's a sum statement, you only have to find one case when it's true, and it becomes true. If it is an all statement, you have to show it for every single one, and you would only need one counter example. So those are the big pieces, I think, as you kind of look down in the homework, you will be asked to look for if-thens, if and only ifs, and the mathematical connections. Let's see here. I don't think I have too many of these, so I'll probably make a separate video for those in case you want to think about those. Right? Yeah, so if you were doing homework, ooh, let me check and see what homework I actually put here. Doop, 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 doop. Green cat, go to the homework. Homework chapter 2, 1 through 2, 1 to 2. Okay, that's just, is it a statement or not? Use quantifiers to make each of the following true. So that's where you would say for all natural numbers, for some natural numbers, or for no natural numbers, okay? So it's either all, some, or none for those. It's 1 through 2, 4. Write the negation. Okay, so write the negation of this statement. You've got regular statements. You have some quantified statements. Let's see here, 4, 5. Identify as true or false. Okay. And let's see here, 8 through 10. 8 is Q stands for it's goodbye. Write each of the following in symbolic form. Okay, so we're translating into symbols. That's good. Okay, so make sure you have some practice with that. Probably question 13 might be a challenging one. If you build it, they will come. So P goes to Q. If you don't build it, they will not come. So again, negation of P goes to Q. If you build it, they will not come. P goes to not Q. Okay, so that kind of idea. Those are the statements where you want to practice writing them in symbols. Sometimes it's easier to see it in symbols. Okay. All right. I think that's going to wrap it up for this section. So I'm going to stop sharing and say, hey, thanks for this. I will make a second short video on 2.1 math connections. So we'll do that coming up next. All right, off you go.